Hello, we are going to talk about energy in elastic materials. So, you talked about energy in other context. Elastic materials are modeled with spring-like behavior, right? So, we will look at a spring first. So how do we think about energy in a spring? You probably learned about potential energy and other things. Let's review just a little bit what the spring looks like from this perspective. So I have a spring with spring constant K, and I'm gonna push on it. I just put a plate here so I can conveniently push. So I push on it, and then I push all to the X, and I kind of put a stopper. And the spring is in a compressed state compared to this original, right? We say the spring is holding energy. Our spring is stored energy. Where does the energy come from? Well, think about it. Well, if you are the one pushing it, you were the one who gave the energy to the spring. You did work on the spring, right? So your work on the spring is from the conservation of energy. You would expect the energy that is stored there is the work that you did. So how do you figure out how much work I did in compressing the spring? Well, you can see that force with a displacement, if the force was constant, then this times this will give me the work done, right? But here the force is actually changing. The more I compress, the greater force I need. Like right now, when it's just the zero, I need almost no force to compress, right? Very tiny amount of force to compress. But as I compress more, the spring's force goes up against me. So if I plot the force I will need versus how much I'm compressing, and say I use this x-axis just to make things easier, all positive. So I'm going all the way to the positive, the x is positive. So if I go all the way to the point called x, from x equal to 0 to x equal to x, I'll get a plot like this, right? So this is the force, and the slope is k. So at the very highest, at this point, my force is kx. At different points, my force have been different, right? Then I see that the force is actually a function of the displacement coordinate. In that case, I need to do the area method, right? We need to do area under the curve because work will be an integral, and I need to find the integral. Another way to do the integral is think in terms of the area under the curve. In case you are not using calculus in your head, then you can bypass that integral thing by just looking at the area under the curve. So the area under the curve is very easy to do. It's kind of triangle area, which is half. This height is kx, and the base is x, and so this is the amount of work you did. That's the amount of energy that is stored here. So we would say energy of the spring is half kx squared. This is a very physical way of thinking about where the energy in this spring comes from. Okay. We can do exactly the same thing for compressing some material. Say I take a material of area of cross section is A, area is A, length is L. I do exactly analogous experiment. I push. So I want to figure out how much work this will do when I'm pushing. Turns out the more I push, it's just like there, I need more force. So if I look at external force and plot versus delta L, I will get a very similar thing like that. Turns out, because force is, the stress is force over area, and stress is also y times epsilon, right? This is Hooke's law. and this is just definition of the force and stress. So I can write force as a sigma times A from here, and epsilon is delta L over L. So I can just use these and see the force is actually this expression. So if for a particular delta L, like over here delta L, the maximum force when I compress all the way here is y times delta L A over A. So that's the point. So I now know the height is that. I know width is delta L. So this triangle's area is half height times width. And you can now see that I can really manipulate a little bit. So I don't want to keep delta L because in a material, it's not the change in length that's the right property. The right property is strain in the fractional change in length. So I need to somehow convert these guys into, there's a delta L over there because of the way this diagram worked, right? Work requires F dx or F times delta x, right? So F force displacement. So this is the displacement. So we want to, this is okay. This is in the right strain, right? And so this one needs to convert the strain. So I can divide by L and then multiply by L over here. So this can, and I can write delta L over L in the symbol of strain. This is strain. Then I get y times AL, and I can write these two together, can then combine them, and this epsilon square, just like x squared. X was the associated with the deformation. There it was displacement, but here I am writing it in terms of the strain. So I see this is very similar property. This is like K and this is like X, but they're just analogy. They're not same units. Actually, I have to multiply by the volume of this thing. I need to multiply the volume. So this whole thing is area. This volume times this whole thing is energy, right? Then this stuff over here, I might think as energy per unit volume. Energy per unit volume, or energy density. Cool, right? You have a density, which is mass per unit volume. Then you have a property called energy density, which is energy per unit volume. So if you haven't encountered energy per unit volume, this is a nice place to say it. When we write this, we say that this is the elastic energy. So the elastic energy in this system, elastic energy that got stored here is when it's constrained. I should write over here elastic energy here, elastic energy here. And there's no elastic energy there because it's in the original length. Elastic energy here is half y epsilon squared times volume. Well, this is for the length, right? And we have studied other types of strain and stress. Like if I had a volume and I compressed it, right? This will be very similar. You'll have a bulk stress and bulk strain square times the volume. Shear energy formula all also be like this. This is a universal formula for all kinds of strain. So as long as the strain is not too great, and you are in the elastic region, you are in the linear elastic region, So if the normal object is this big and you just tiny bit you change it, right? Then how much extra energy is contained in that? That will be given by some kind of modulus. So let me write down this formula. More general formula will be half times some modulus times strain how much percentage change I cause squared times volume. Okay, I hope you can appreciate this, because we are going to use examples of this in some numerical problems. So take care. Okay, see you. Bye.